Good day to you. This is Galactic bringing you a special presentation of a formal proof. This will be along the lines of Alan MacDonald, a very well-renowned geometrician. Although he deals in mathematics, he has a geometrically oriented mind. A great advantage in modern physics is to know geometry. That's what I'll be talking about today. Over here you see two interacting bar-type spiral galaxies. I made a special study of these and studied over 400 of this kind of interaction. Alas, that work was lost in the campfire. However, I did have a database filled with 1,000 galaxies, so I'm a galactic astronomer of the analytical sort. I study structure. Ever since a few years ago, I became interested in the mathematical side of astronomy, which gets one interested, I found out, at least in my case, in astrophysics and the latest discoveries in deep space cosmic science. This would include all galaxies and any units higher. There are such things as clusters of galaxies, of which I'm sure you're aware, because dark matter was first discovered that way was by studying galaxy clusters. And then later that work was revived in the study of the gravitational profile, as it is thought to be, of a spiral galaxy. It is now possible to use spectroscopy to analyze the light curve, which distinguishes two sides of a spiral. If it's oriented correctly for this kind of a measurement, you can detect not only the overall light profile of the galaxy, but also its rate of spin. And by taking segments, which is now possible to take segments to divide up a spiral galaxy oriented correctly for this type of measurement, it is possible, as did Jocelyn Bell. I believe I've gotten her name correctly. She followed up on the work of Fritz Zwicky, who did his work on the Coma cluster of galaxies. This was about a decade later, a very rough estimate. In the 1960s, I believe, it was Vera Rubin who discovered. Jocelyn Bell is another distinguished name in astrophysics, astronomy really, and astrophysics. But it was Vera Rubin who revived the work of Fritz Zwicky, who awarded the name of what he had to assume that he had discovered, dark matter. And what dark matter is, quite simply, is a placeholder for an apparent deviation from the Newtonian gravitational potential of a galaxy. It should have a light profile showing its relative velocity from one side to the other. One side would be rotating toward us, the other away from us. But you can now take segments to find out how that gravitational profile, as it has to assume to be assumed to be, it does not conform to Newtonian mechanics, nor indeed to Einsteinian mechanics, which in this case would not be a tremendous difference, since the gravitational profile of the object is quite localized, at least in galactic space, or in the case of Zwicky's discovery of, you could say, supergalactic space, since it's more than one galaxy in a cluster. Between 100 and 1,000 is a very rough estimate. They tend to be around 300 bright galaxies per cluster. These are the building blocks of the universe at macro scale, thus far discovered, although there is more being discovered. And indeed, huge large quasar groups, and that is actually their name, you can look that up. It's usually abbreviated, rather mercifully I'd say, HLGC, which is huge large. It's because large had been used and then there was something much bigger. But these are quasars, by far the brightest things in the universe, which are now known to form some kind of structure. Computers identified this, and it's now confirmed. that quasars, which are quite distantly spaced, do form large groups, which defies certain modeling. So that's why I have this picture over here, but today we're going to be discussing something just a little bit different. This is where we left off a few presentations ago, where I'm attempting to wrap up several threads, but all of it led to the geometry of the universe, which is my specialty. A rather grandiose, I'd have to say, portrait of a field of endeavor. The geometry of the universe is a very real thing, but one would have to say one would have to start closer to home to get some idea of the geometry. I would just put it of cosmic units going out further than we're capable of defining so far, because new discoveries have been made recently in terms of decades. The huge large quasar groups were discovered in this millennium, so it was only with the advancement of telescopy, which is a real word, the science of telescopes, which is quite a science. We've increased our wave band reach, so we can now use radio astronomy, X-ray astronomy. There are advanced forms of astronomy, that is telescopy. The James Webb Telescope, as you're probably aware, does cover the visible light spectrum, which is always an advantage. You want to get that, although you can't if you're using an X-ray or radio or even sub-infrared telescope type. The James Webb Telescope does have a wave range, a wavelength range that reaches into the optical spectrum, so we can see the photographs by looking, but you can superimpose other wave bands, and that is done to great advantage now, so we can see more of the galaxy in forms of light that our eyes are not capable of detecting, but which our instrumentation is capable of detecting. But in the case of the interacting spirals that I just showed you, that is plotted, that is to arrive at the concept of dark matter, which I'm just going to cover briefly because it's so often brought up in cutting-edge science. In the popularly available forms of astrophysics, dark matter is a very, very strong topic of interest. For very good reason. Dark matter has really stumped the band, but all it is a placeholder for the flat plate spin, which is now commonly adduced to be the gravitational profile of a galaxy, not as expected, not according to Newtonian, Einsteinian, either formulation of gravity. The spiral galaxies being measured since the time of Vera Rubin, and it's been well over 50 years now since most of this has been known, and recently, of course, more and more. The James Webb Telescope is capable of taking extraordinary photographs which reveal more information, but nothing has changed in the assessment of dark matter. Dark matter, as you know, is the subject of intensive research, and it's fair to say that most of it is mathematical. But it can't be just mathematical, because we're seeing a physical phenomenon that does not match what we expect from our equations for gravity. There are more than one type of equation for gravity. Newtonian and Einsteinian are obviously different, but nothing is different in the view of this gravity profile for galaxies, that they have a gravitational, you see, it's thought that it is gravity that is controlling the spin rate, and therefore you would expect the inverse square law to apply, that what's rotating at the periphery of the galaxy, relatively speaking, not close to the center, to be comparing the more central rotation to the more external rotation, but still part of the same object, called an extended object, because it's made, you would have to say, mostly of stars. But what was discovered is it may not be as mostly made of stars as we thought. There may be some non-luminous material. Well, we already know there's some non-luminous material, but from our analysis of our own galaxy from the inside, which is an advantage here, but we can say that we are fairly certain of the gravitational profile of our own galaxy, although that's worth checking into yourself to make sure you understand what has been discovered about the rotation of our galaxy. The measured rotation of other galaxies that we're seeing from the outside can be presumed. It is a hypothesis that what would make that rotational profile based on pure gravity, nothing else, that the assumption of non-luminous matter, it would have to be distributed in such a way, but then it simply is imagined that there is this dark matter. Dunkle Materie in German is how Fritz Zwicky named it, and he did name it that. I did go back and check, in fact more than once, because of the way that that notion has been extrapolated is in fact purely mathematical. It's based on the formula for gravity. And the formula for gravity predicts the inverse square law, and that does not pertain. It's a flat spin. It's like the whole thing is a plate and it's all rotating as one thing, which obviously does not conform to an inverse square law. There's something else happening, and the assumption of this dark matter is thought to compensate for our predicted gravitational profile, which is now known does not match. So some explanation must be offered for that. The only one that I've heard of, it's not the only one, but the only one in a certain sense of being acceptable in any way, is the first hypothesis that it was Zwicky's name, at least. I was most curious to know if he had any other hypotheses alongside, because now there are other hypotheses. One of them, rather abstractly I would say, is called MOND, which means modified, that's the MO, and then the ND stands for Newtonian dynamics. So it's modified, that's the MO, because MOND is something you can pronounce. So sometimes it's actually called MOND, similarly to how the theory of everything is sometimes thought to be objectionably disrespectfully pronounced toe, which yeah, well, that is what those letters spell, so that is a mnemonic which does assist us as, just humans. But toe, I mean, well, theory of everything is that kind of an acronym. But in this case, MOND, the first two letters represent modified. So that is one alternative. It's not, there's more than one of those. So when you say modified Newtonian dynamics, you actually have to be specific. Which one of those theoretical, it would be called a model in this case. You're trying to model in some way. It's rather disturbing, which is why because we expected that all galaxies would have this kind of a gravitational profile. They don't, and that's really quite a challenge. So you've got to explain that. That is, you must try. It is considered requisite at the cutting edge of physics, which of course somebody is going to be trying to theorize about, to make some prediction on which way to look or what's most likely. Natural selection was based on this. In fact, the supposed passage of the chariot of the sun across the sky every day There was another theory which was finally shown to more adequately explain the passage of the sun through the sky every day that's not necessarily a chariot, or that the entire thing is revolving around the earth. There's a much better explanation. Well, what we're looking for is a similar, much better explanation for the gravitational. You see, it's not even certain that it's gravity now, because it doesn't match. Well, if you insist that it has to be gravity, then, which apparently Fritz did, which surprises me. He's one of my teachers. So what we're going to get in today has nothing to do with that superficially. That is, the rotation rate of galaxies and what that means for Newtonian dynamics. But I thought you might want to know why I very much enjoy having this photograph up in the upper corner. But what we'll be talking about is not even related to what you saw there. So I'm just going to turn this off and show you something which you just need to know that I just wrote this today, but this is the result of quite a bit of thought. And I just want to show you this is what I'm going to be talking about. What's at the top of the page, all the way to what's at the bottom of the page. I'm not sure if you can see that clearly, but don't worry, I'm going to read it. So these that I will be discussing are the numbers. And the numbers, of course, are so basic that I wouldn't blame you if you kind of reflexively did a ho-hum. Actually, this is extremely important, profound, and basic. What are the numbers? Now, without going into what would be called number theory, I'm going to summarize what I just happen to know is true. So you do have to trust me. I hope that you consider me trustworthy. If this is your first time tuning in, you have no reason to believe that, and you shouldn't. A scientist trusts no man, only the proof. The first item on the agenda is why in the world do we need to talk about the numbers at all, when what we're after is, for instance, something like quantum gravity, which is one of the most sought after goals, is quantum gravity, or even the solution or some solution to the quantum paradox, which has stumped the band for a century. Something like that. I am leading into these topics. Also, dark matter has a most interesting explanation. According to what? According to a reinterpretive geometry. It is a remarkable fact which bears emphasis, so I will state forthrightly that geometry is the gateway to understanding, and always has been. I suppose that could be debated to effect, that is, to have more than one mind focusing on that topic, because you're just hearing my side of an issue which is actually profoundly deep. It's the relationship between geometry and numbers. The relationship between geometry and numbers. Because it's worthwhile to restate, just for the record, so to speak, that what science is seeking in its measurements, really we only have measurements. Now you could say you look at a photograph of distant galaxies, that's a form of analysis, is your visual. Well, that's geometry. What you're looking for are patterns such as you saw. And I'll just refresh your memory. Those are obviously geometric patterns, correct? They're curved, which is what you would expect in outer space, wouldn't you? Not straight lines. Although, I just want to draw your attention to one other item, which I am about to capture here. That's the Pleiades. That's the curve. There's this. There it is. Now you know that I like to show this, and I won't show the whole thing, but you know that that is a double radio-lobed active galactic nucleus, and that is curved, but you can see it's also straight as it comes out. It's a bipolar jet of subluminal material that's blowing out into those plumes. I'm just going to expand it just a tiny bit here. Is blowing out into plumes that are kiloparsecs in, you would have to say, diameter here. There's one plume, and here is the other plume. I'm going to get a little bit more so you can see this. Those are two plumes. The upper left-hand one, those are kiloparsecs in length, which you can just think of as thousands of light years. That's galactic scale. So these are no small jets, but that's a linear phenomenon on what you would have to say is, you see, it's not perfectly straight because it's rotating. That upper left-hand plume is rotating toward us. You can see it's brighter. And the lower plume is rotating away from us. Well, that's geometry, and that's really all I wanted to say. So there is geometry to consider just when considering a photograph, but we do want measurements. Those measurements that I gave to you, that this has a known speed. Those jets are traveling at a speed which has been measured fairly accurately, and they're obviously oriented as bipolar jets. Well, how far do they go? That's been measured. We know how to make those distance measurements as well. We can also tell that it's spinning, so it looks like it's the birth of a spiral galaxy. Well, it's geometry, so that's the point that I'm trying to make. But we make measurements with numbers. So we do need to know what we're doing with numbers, and that's what I'm going to cover today. So we have a firm, sound basis in numbers, numerics, going to math. There's arithmetic, math, algebra, and even the calculus, which is an interdimensional operator, as I'll be showing you. We need to characterize space with a metric. That's summarizing a whale of a lot of information, which Alan MacDonald would insist on going into in detail, but I've done that in prior video lectures. And again, you do have to trust me here because I'm summarizing a rather enormous amount of basic information into a few gentle rubrics so we know what numbers are. Well, what are they? They're applied as a metric to a space, which is generally conceded to be, or had been, spatial space. The space is used in two ways. There's physical space, but a geometric space is a construct of the human mind. Essentially, the objective is to get a match. And that leads us to our topic rather swiftly, which is, do our numbers match? Well, what's the geometry of the numbers? That's what we're going to cover. As you're probably aware, the correct term for our form of mathematics is linear mathematics. And why? It's based on the Euclidean definition of the line, which I've covered very recently again, so that you're fully aware at this moment, as I trust, what is a Euclidean line and what is the modern interpretation of that as the numeric basis of all of our mathematics. It is linear because it's based on the Euclidean line, which has an additive identity at the zero, at the null. The center point of the line is balanced on two polaric infinities on plus minus, which is an operator, the most basic operator of all, which defines the metric of spatial space using a linear axiomatization of space, which begins with a straight line, and rightly so, because that's where our numbers are. So the zero was discovered last, but it is now known that it is consistent to have a zero at the center of the line for the operator addition, because that's the definition of the metric of linear space. And then that advances with the use of 2D and 3D and finally 4D for spacetime. That's systematic linear space, which cubifies space. In 4D, it's hypercubic. In 3D, which is a very common term, is cubic. And these are also mathematical terms. Cubic equations apply directly to this phenomenon, or I should say construct, of the human mind. If you go down to the plane, to 2D, then it's two lines at orthogonal angles, and that's the definition of the geometric operator, its orthogonality. that gives us systematic space, beginning with the one-dimensional line, because the point that Euclid defined is now known to be 0 linear dimensions, which is a very interesting property of that point, is that it has no dimensions. Numerically, that's 0, and that's extremely important to have a direct insight into that. It's because of the line requires the 0 to get the metric, whose index is 1. That's a huge amount of information summarized, but this is the time for synthesis. So the metric of linear space is the linear jump from 0 to 1 that gives you your smallest unit of measurement for distance, which technically is linear spatial separation, and that's real space, called distance. Also, it's length, but it's always called distance now. We don't use the word length normally. For engineering, you might, but not in deep space, not for cosmic science, not in quantum mechanics. It's distance, not length. So they're virtually synonymous because they rely on exactly the same axiom for everything that I just described to you. So that is the basis of linearization of space, which is an extrinsic geometry. What I discovered is the intrinsic geometry based on the only other object that can parameterize space either geometrically or mathematically, that is, numerically. Now today we're going to talk about the numbers, because numbers are so critical to everything we do in science. It's just inescapable. Then the linear number system is an extraordinary system. It is the basis of numbers, and therefore linearization is a very natural step in science, in logic, in geometry, and in numbers. Is to use linearity to parameterize spatial space, is to parameterize space. And that was accomplished long ago, over 2 millennia ago, with the concept of 3D. And this, of course, is the planar space, which is simply an infinitely large flat object of the mind. That's what a plane is. But it is worth noting that that is how we see. And that's why a movie or a computer screen looks so realistic, virtually, that you can't tell the difference. It's because you see a flat screen. Well, how is that space, which is now a flat plane in the mind, how is that parameterized? Well, first you would have to know what that word means. It means applying numbers to your geometric space. In this case, it's a geometric space. If you start with 0 linear d, then you can very logically extend the points onto a line by which you get 1d, and all of this can be retroactively proved on a watertight proof that as long as you're using the operator add, then 0 must be at the center of the line, but of nothing else. It's the numeric center of the line, as we now know. It took a long time to figure that out, that 0 is equivalent to Euclidean null. At 0d is also 0 the number, but it's a linear number, and that's going to be critical because there is such a thing as spherical space, and therefore there is such a thing as circular space. But if you apply the circle to the plane, that is not this. You're not starting with a line, because the line is open, goes to 2 infinities. The circle is closed, so that has an exterior and an interior. That's quite different, and that is the difference between closed curvature and open linearity. There's a range in between that I covered in a lecture just given yesterday on the evolute of the line into the circle, which Kepler studied. He drew diagrams of this extensive. What happens when you have a line, and for instance, you just draw a circle that's tangent to the line? Can you conform the straight line to the circle by a transformation? Well, if you do, the first thing you get as you start to curve the line toward the circle, it's a hyperbola. And then it will reach a very interesting balance form called the parabola, which is just a single thing in this construction. It's a whole family of hyperbole that are hitting infinity at a different you could say angle. But when it reaches a certain limit, it is now balanced, and you know that because if you keep going, it collapses. That's the collapse of the wave function. I'm just throwing that in to show you that this leads to a solution vector for quantum mechanics. This will solve for the collapse of the wave function if I can describe to you this transformation called the evolute of a straight line to a perfect closed line. A perfect rate closed line is not an ellipse. That occurs obviously in macrospace. The planets describe elliptical orbits, which is very interesting to consider because an ellipse is very similar to a circle, but a circle, of course, is a perfectly symmetrical. It's no longer an ellipse. So what happens when the hyperbola is lifted off of the straight line to try to close on the circle? It reaches the parabola and then snaps. Now what it snaps to would be a line orthogonal to the original line. So it snaps to a orthogonality on the closure, and then if you continue the impetus or the momentum of that, called a transformation, the line will turn into an ellipse. And the ellipse will then, and it's elongated this way now. It is elongated vertically, so it starts as a straight line, and then because you see this motion, this transformative action, when it reaches the parabola, something happens. It just changed from a hyperbola, which has a specific mathematic formula in 2D space. It changes to a parabola. It's no longer part of the family of hyperbole that were fanning up until it reached the parabola. And what happens next is that the two infinities, there are two linear infinities that are being bent upwards simultaneously. When they reach the parabola, you could say that you can't go any farther. But if you force it on a continuum, it jumps, and that's the quantum jump. So you're seeing the collapse of the wave function and the quantum jump. And I'll leave it at that until I can more fully explicate that, as I have done in the past, but this is synthetic so you see it all. And now we need to turn to the numbers. I just wanted to give you some visual clues as to why we need to understand the numbers. First of all, that 0 is peculiar. It is the balance point of the line, and therefore it's the balance of the integers. And if you think of the integers as going to two infinities, they're polarically, they're 180 degree opposites. But they're equivalent in both directions. So even if you go to infinity and say you've hit either 1 or 2 points, and that's an interesting distinction to make, is this hitting one infinity? It is in circular space. It's hitting one infinity. It's the line is making a circle. So the line is the derivative of the circle, and that can be proved, and I did prove it, so that is known. So that's an interesting relationship, that the circle is a closed line. It's perfectly balanced between the vertical and horizontal aspect. So it has a perfect rate. And that is why E is used so often. 2.718281828 4 ... To give it, I think that's 9 decimal places, 10 actually. But it's a number that's fascinated mathematicians. Surely Richard Feynman certainly made it famous. But that's a perfect rate between two orthogonal axes. So that is how we normally parameterize the plane. So what does parameterization mean? It means applying numbers to your geometric space. When you do that for the line, you get all the numbers. All numbers. Any number system. There are about 8 counted linear number systems, beginning with the integers, counting numbers, natural numbers. Rather interesting distinctions between these. Then the proportional numbers, a very significant, called the rational numbers. And then the algebraic numbers, of which there are now conceded to be 3 classes, which is now in a Venn diagram. because all of these number systems are based on going right back down to zero. Zero is at the center of all the number systems, but I'll show you today it's actually not. It's not the center of the circular number system. And I'll show that to you now with a brief discussion of the computable numbers. The computable numbers. This goes to machine logic, and your CPUs, your computers, use a form, it uses a number system. Well, you know what it's called? Usually it's called the binary number system. And when defined correctly, that is absolutely right. Well, what is that? What is the binary number system? If you represent it with zeros and ones, which is how it is representable, with zeros and ones meaning basically electronic on or off, well, that forms a true-false system on which you can construct a number system. But you can't give it just any number. It can't represent just any number in the Venn diagram. It can only represent a subset of the linear numbers. And that's a number set, which is the true definition of the set. A set only applies to numbers, and then it makes sense. A set of numbers. So a set of numbers would be something like the natural numbers, the integers. The rational numbers is a set of numbers. Well, it turns out that the binary number system, on which all of our computational, really miraculous amount of information can be represented using binary. It's creating the image on our screen, which I'm looking at now and you'll look at later. It's all created with binary numbers. So what are they? As you know, the first binary number, the lowest if you don't count fractions, the first whole number in the binary number system is 1. After that, there's 2. And nothing in between, because this is machine logic now. It is binary in the sense of being representable by an on-off binary state. It's one or the other. It's either one or it's not. And that works in electronics to create circuit logic, which creates the capacity to create a Turing machine called a CPU, and it's you could say its lowest number, not including fractions. We're getting to the fractions, but I'm following the Alan MacDonald strategy of being absolutely leaving no loopholes open here. So the counting numbers are the superset of the greater than 0. Am I saying that right? Not greater than 0. The first whole number in the system, as with a linear system, is 1. But then it changes. And not right away, because the next linear number that can be representable, these are called the machine representable numbers. Almost simultaneous with computable, and that really is the point of each expression for this kind of a number. They're the representable numbers, and therefore they are computable, because you can represent them in machine logic. And you get the binary number system, which basically has 2 aspects. The numbers less than 1 and the numbers greater than 1. 1 is peculiar. It is the lowest counting number, which is also true in linear mathematics. There is no counting number by definition, by axiomatic. Well, that's because 1 is the index of linear spatial separation. There's no number less than 1 for the index if you say that the index is indeed the smallest. Well, that leads to an interesting paradox. What is the smallest spatial separation that you can measure? In quantum mechanics, that is called the measurement problem. So from many angles, we're closing in on the quantum paradox, and we'll also be closing in on what makes this the way it is. It has to do with geometry, but you have to now understand there are 2 ways to parameterize planar space, because if you just conceive of it as a blank sheet, which is how we see, what's the shape of its edge? Well, what I proved in 2022, you could say it's been always known, but it's for space, the space we actually see and can measure, it's spherical, because it's the same in all directions from a center point. Well, that's a different definition of the point. It's very interesting that the center point is constructed differently. This is our lab cat. She's here to remind me I need fluids. She watches over me, or under me, depending. Oh, there she is, my beauty. She is my beauty. Do you know where the camera is, honey? She's not really. Yeah, she wants attention is what she wants. She loves me. Well, I love her too. So that's a lab cat. Most necessary part of this operation these days. There you can see her ear. Okay, I don't want to get gushy, but that's 40 minutes. In the next video, I'll complete this McDonald strategy approach to what is a number by discussing the numbers less than 1, the highest of which is 1 over 2. And that, as you know, is the wavelength frequency relationship. 1 over 2 to 2 over 1 is light speed. We'll be right back. Very good. This is the second part of our presentation. If you haven't seen the prior, I recommend seeing that first, although I do like to keep my videos self-contained. We are talking about the binary number system now, which is a set of numbers, which is a subset of the linear numbers. The linear numbers are one-component numbers, and I trust you understand that statement. There is such a thing as a two-component number. The most famous example of that, and so far the only example of that, is the complex number system, which I won't touch upon today, but I've spent several videos, actually several video series, making sure we all understand both the strengths and perhaps even the drawbacks of the complex number system, which now dominates science. It's the only number system in use, both in quantum mechanics and in cosmology. So you must use the complex numbers or you can't do science. That is contestable, but we're not going to contest it here because we're going to find out the actual basis of all number systems. And that is the goal today, is to discover what is a number. We've come quite a ways, but we can summarize what we know by saying whatever number system we end up using, they must be computable, which means they must be representable on a computer. And that's known. It's the basis of computational science. We do use the binary numbers as the basis of all numbers that are useful for machine logic is what it's called. But you can see it's quite powerful from everything you know about computational science. The representable numbers are the basis of that. It's called the binary number system, which splits quite conveniently into two aspects, which are easily discussed once you understand there's a relationship between two types of numbers in the binary number system. The Archimedean of the system is 1 instead of 0. There is actually no 0 in the binary number system. There is, however, a very important footnote to that, because the way the binary number system is set up on a computer, you do have a double 0. And there's a plus 0 and a minus 0, which you might suspect leads to something of a contradiction. Because shouldn't there just be 1 0? In the linear number system, we have always assumed that there's just 1 0. But when you try to represent 0 in the binary number system using gate logic, also called circuit logic, you end up with the possibility of using 0, but it's not one number. So it's a different kind of 0. It's a binary 0, which is a strange thing to say. In order to see that there might be such a structured 0, that there would be 2 if you try to represent the 0 in a binary number system. Why would that be? Because if you draw a line that only has 1 0, but you see it as a plus and minus 1. And so the characteristic of the index is that it goes in 2 directions at once. One thought to be negative, because that's very convenient for us to think of those as being negative in one direction and positive in the other. But when you do that, it ends up re-axiomatizing the 0, not in the way that Euclid said exactly, because he said it's a point that has 0 dimension. Well, the 0 in the binary number system does have a dimension, and it's interesting to try to characterize why that is not null. It's because null is conceived to be a single component number, but in the binary number system it's not a single thing. It has to be represented in 2. If you represent it at all, it will be represented as a split number. And that is an extremely profound insight that I'm attempting to home in on now so that you'll see it directly. But it is perhaps mathematically most convenient for you to see the proof, and it could be that your mind would latch, or you would see the logic, the pure logic, mathematically rather than geometrically, or perhaps geometrically rather than mathematically. I'll show you both, which should attain closure on a interpretation of the binary number system that it is a split number system. It's not a single component number system. I'm now going to prove that to you. And this may be one of the most amazing insights you've ever seen, because it changes the structure of our number system by direct insight. The representable numbers are the computable numbers. It is the binary numbers, which begin at 1. And that is both the highest number for the fractions, which is 1 over 1, and it's the lowest number for the whole numbers, and it's still 1 over 1. So it's 2 different ones. But this is only talking about what for the system is the center number. You see, it's equivalent to 0 because it's the center number. But it's the center number how? It's the center number for proportion. It's not division and it's not multiplication. It's most often called the multiplicative identity, which in mathematics does make sense to call it that. But it turns out, you actually have to look at that again. Is indeed the binary number system a single component number system? I'll show you that it's not. It's actually a 2-component number system, and here's how you see that. If you begin with the counting numbers rather than their reciprocals, which would be the fractions in the system, beginning at 1 over 2. Why would it begin at 1 over 2? It's because that's the next counting number. So, and it is a binary number. 2 is a binary number. It's representable, and so is 1. So you can put them in relation, and that also is representable. 1 over 2 is representable to the same proportion as 2 over 1. And those are the actual numbers that are being represented. That has been proved. I proved it. But it had been proved before. I just proved it in a new way. So if you need those proofs, leave a comment. It's difficult to consult my 960 videos because they're not indexed. But this has all been covered before. It's also been proved, not just by myself, which would raise a red flag if it's just been proved by myself. That's bypassing the scientific system, the scientific process, which requires review. It has to be more than one mind that sees the same thing, or it's not science, correct? It has to be communicable. So, to say that the binary number system is a 2-component number system, you could say that it's well known because it certainly is basic, but I've never heard it said, certainly not often enough. So I'm saying what I believe is the most important thing to say about the representable computable numbers. it's virtually synonymous, because in order to be computable, they have to be machine representable. And so it's more basic to say that they're the machine representable numbers, and that is the binary number system. But the lowest counting number is 1, which I keep saying that, but what's the next number? The next counting number is 2, and that's also binary. So that's representable. Is 3? Yes, but pause right there and look at what 2 is. Because what I'm saying is that 1 over 1 is the lowest counting number. And that is a 2-component number. 1 over 1. That's proportion. Don't think of it as division or multiplication, because the comprehensive term that describes both, as the operator that we were taught, it's the multiplication division paired operator. Well, as a pair, that's proportion. So that's different from the line. So it's pertaining to a different object than the line. That's quite a critical insight, which you're now going to see, I hope. That's my goal, is to get you to see this. So see what? To see what happens next. When you start at 1 over 1, accepting my hypothesis that that's the right way to state it, which you could certainly say it's not contradictory in any way, 1 over 1 is the lowest counting number in binary. Well, the next number after 1 over 1 is 2 over 1. And the reason we know that that is consistent is because the reciprocal is also representable. So if you take 2 over 1 and you invert it, you get 1 over 2, which is also a binary number. Now you may sense the problem that's coming up. In binary, you know that the counting numbers are counted in powers of 2. You know the reason for that? It's because if you go from 2 over 1 to 3 over 1, which would be the next linear spatial separation single component number, is 1, 2, 3 is the next in order. In linear space, it's 0 to 1, then 1 to 2, and then 2 to 3, and then 3 to 4. In binary space, there is no 0, because you can't divide 0 by 0, so there's no representable number for 0. There's an interesting footnote to that, because the system does have a 0, but it's a split 0. There's a plus 0 and a minus 0. Now that's a lot of gobbledygook, but now I just want you to watch. 1 over 1, the next counting number is 2 over 1. Now if you go to 3 over 1, now invert it and see if that's representable. That's 1 over 3. Is it representable? It is not. It is not a representable number. And that means that 1/3, what we consider to be a perfectly ordinary fraction, is not a computable number. And the way you state that mathematically is that it has a repeating decimal. That's much different than closure. It's not quite a linear number in the sense of being computable. So we're not talking about the linear numbers, which do include the rational numbers, including 1 over 3. But in binary, 1 over 3 is non-representable. Therefore, it's not in the system. I hope you accept that, because it's extremely well known. But stating it the way it needs to be stated can be quite a challenge to the mind, because you're starting to sense that maybe you've been given some contradictory information about what is a number. I simply want to clarify for you so you know absolutely certainly, without any shadow of a doubt, you'll always be right if you define what a number is the way I'm telling you to define it. Because the basic number system is binary. So it has two aspects that are in dual. When you have 2 over 1, that is a representable number because it's also representable in its conjugate. We call that the reciprocal, I'm going to show you that there's a geometric relationship between 2 over 1 and 1 over 2, the two constituent basic numbers of light speed. I hope you see that. That's throwing in quite a bit into the mix that was technically unnecessary, but I want you to know the significance of this. This does affect our definition of light speed, which therefore is going to affect our definition of space-time. It's much deeper and much more fascinating than that, though. And this is a solution vector. So, the 2 over 1 is representable, but 3 over 1 is not. And so the next number after 2 to the power of 1 is 2 to the power of 2. And then it goes in exponential form. 2 to the power of 1 goes 1, 2, 3, 4, 5, 6, 7, 8 to infinity. And that is the linear set of positive numbers. They're positive counting numbers in power space. In power space. And we write that as 2 to the first power. Do you know what the representation is of 1 over 2 in power space? It's 2. What is it? It's 2 to the negative 1. So the positive and negative integers in power space form the exponential space for the base 2 system, whose number is 2. But we know there's one lower number. Well, what's the lowest number in linear counting space? It's 1. But we know there's one less number for that, 0. In power space, the starting number, the index, is not 1 as it is for linear spatial separation. The jump from 0 to 1 is the index, as we just discussed. It is quite synthetic. I hope you're getting this. Rewind it and listen to this again if you need to. So you begin with 2 over 1 and then 4 over 1. That's 2 to the 1 and 2 to the 2. So we're just going to leave out the number 2. And we're going to restart the system with 1 at the center. And 1 is at the center because the jump is no longer from 0 to 1 in power space. The jump is from 1 to 2 for the representable number itself. So if you say power 1, that's the number 2. What if you say power 0? That's the number 1. So 2 to the 0th is 1. But it's ambiguous because there are 2 zeros. So it's 2 to the 1, split 2 to the negative 1. That's 2 over 1 and 1 over 2, which multiply to the center number. So instead of plus 1 and minus 1 adding to 0, plus 1 and minus 1 in power space multiply to 1. And then 2, those two numbers, that would be 4 over 1 and 1 over 4, another valid frequency wavelength relationship because they're reciprocal, they multiply to 1. And indeed, the next pair in power space linear, and now we've recovered 0, but it's a power 0. So it is a structured 0. So if you say 2 to the 0th, is it plus 0th or minus 0th? If it's 2 to the minus 0th, you get 1 over 1. But if it's 2 to the plus 0, you get 1 over 1. Is there a difference? Yes, there is. 1 over 1 is equal to 1 over 1. But how are those equal? Because it looks the same, doesn't it? Well, are they the same? One is 1 over 1. This is like 1 was 1 racehorse. 2 was 1 2. 1 horse race. 22112. I hope you like that little ditty there. So now you see in power space we have the integers including 0. But the 0 is not structured the same. You get 1 over 1 as the result. The numeric result is 1 over 1. But they're obviously inverted. So you have 1 over 1 and reverse it. It's still 1 over 1. Now I'm going to show you something that if it doesn't blow your mind, you shouldn't study mathematics at all. But don't be afraid, because in a moment you're going to know more than your mathematicians have learned in 2,500 years to the present day. I want you to watch very, very carefully what I do next. We now know that if you begin with a line, you get single component numbers whose center number is 0. If you begin in power space, the center number is no longer 0. The center, these are the actual numbers that come out, okay? The lowest number is 1. I should say the central number is 1. It's not a matter of lower or higher, but you'll see in a moment it is. It's natural. Everything's natural, but this is a much different way of looking at things. That if you begin with a binary number system, which are the representable numbers, which are the computable numbers, we've just proved that 1 is split. But it's numerically the same. That's a magic property of 1. So we're just going to accept that because it's definitely true. But what about 2? Well, 2 in binary is a split number, as we just carefully discussed. 2 is a 2-component number. It's not just 2. You can represent it as 2, and that is consistent. That is the number 2. It's 2 over 1. But the only reason it's representable is because 1 over 2 is representable. And that's profound. Let's go on. 1 over 2 and 2 over 1 multiply to 1 in the same way that plus and minus 1 add to 0. So this is a geometric extrapolation. Is there a geometry for binary space? There is, and it's called the circle, and I discovered that. That is unknown, is that we just discovered a new geometric object that replaces the line. It's the circle. And binary number space is not linear. It's circular. That's why you have to skip 3. You have to, can you skip 5? It's actually a little more complex than just the odd numbers. But is 1 over 6 representable? No, it's not. And you should figure out why. Is 1 over 9 representable? No, it's not. Is 1 over 5, we skipped 5, is that representable? Yes, it is. And what's the difference between representable and non-representable? No repeating decimal. There is a form of repetition where it doesn't repeat the same digit. It repeats what appears to be a random scattering of digits to infinity. And that's called irrationality. That does not exist in the binary number system. So there is no irrationality to the computable numbers. The representable numbers, the binary numbers, are circular numbers. And now I'm going to show that to you so that you see it geometrically. You have a center number of 1. Well, that's not 0, so it's not a point. So you don't have a point in the system. The numeric system has no point. What does it have instead? I'll show you. How did you get the point numerically for the line? I showed you. You add the two polaric infinities. They're called antipodal infinities, but it's strictly linear space you're talking about. So it's the diameter of an embedding space. That line technically does not exist it's useful because we measure spatial separation with it. But is space separated that way? No. And Einstein proved that. Space is separated non-linearly because of time lag. So a distance is an illusion, and we know that now. It really baffled the minds of the early mathematicians when they encountered Einstein's general theory of relativity, which is now applying special relativity in a much broader sense. That's why it's called general. But it changes the aspect of spatial separation. Because of time lag, you can't get an accurate spatial separation in a certain mode where you need to coordinate what's going on far away from you with light-speed transmission signals. For instance, to your Pioneer craft going to the outer planets, you need to talk to it. But when you talk to it with light, and it takes time for the light to arrive. And nobody knew that. Nobody knew what that meant. Well, Einstein showed that it has a geometric significance. And the result is space-time, which is a geometry, although it's quite interesting. We're getting there, but this is the basic geometry that we know works for CPUs, it works for machine logic. It is consistent, but does it have a geometry? It's certainly not linear, because you have to skip 3. You can represent 3, because it's a whole number. It's 3 over 1. All whole numbers are representable, but their inverse is not necessarily representable, and 1 over 3 is not. 1 over 5 is, 1 over 7 is not, 1 over 9 is not, 1 over 11 is not, 1 over 13 is not, 1 over 15 is, 1 over 17 is not, 1 over 19 is not. A prime. If you put 1 over a prime, right? Are there any exceptions to that? 1 over 37, non-representable. The inverse of any prime is not representable. That's the law. I just discovered that while talking. So this is a discovery vector. I just discovered something. Perhaps just for myself. Perhaps it was already known. I would wager that's probably already known, but I've never encountered that unless I forgot it or didn't understand it. So going on, without getting into the intricacies of prime numbers, I think you're going to find, though, that that is quite a clue as to what the prime numbers may be. There's quite a bit of research going on with prime numbers. You may be aware of that. Certainly, if you're a mathematician, you are. So the reciprocal of a prime number is non-representable, and that's why we skip 3 and it goes 1, 2, 4, 8, 16 powers of 2. And there are some computable numbers left behind, but in the construct of what are representable numbers, they're paired. So if you do use 37 over 1, which is 37, right? It is 37. That is a computable number. It's a perfectly fine number. All counting numbers are fine. But if you do use 37, you don't want to take its reciprocal. And it turns out you actually can't, because you're not going to find 37 in the system. Although, see, 1 over 5 is representable, and that's considered to be a prime number for pretty good reason. So I'm not confident of what I'm saying about the prime numbers, but there is something there. That's something to do. So I overstated it just a little bit, and I hope I didn't offend any true mathematicians, because I am not a mathematician. But in this case, I do have certain insight which I need for the geometry that I discovered. It turns out there's a second geometry that's nonlinear, and it is the geometry of the circle. So let's take a look. We're just going to say, let's say the circle has a circumference of 1. Just humor me here. So if its circle has a circumference of 1, but what if it's binary 1? Okay, let's say it's binary 1. Then we know it's a two-component number. And you can just say 1:1. It's 1 proportion 1, but proportionality is non-commutative. So the 1, it's non-ambiguous, or you might suspect it could be ambiguous if there's 1 proportion 1. You can invert that and it's still 1 proportion 1, which means that it is commutative. So why would I suggest that perhaps that's non-commutative? Let's take a look at the relationship between the first. Let's take a look at the first counting number in the system. That's 2. But you know that it's a split 2. It's 2 over 1 and 1 over 2 because they multiply to 1. So they're both representable. So I hope you're following that. Now the next representable number with its paired number, its conjugal number or its reciprocal number or its inverse number, all these terms are used. They have slightly different nuance. But the relationship between 1 over 2 and 2 over 1 is a physical, universal relationship called lightspeed. It's the basis of the formulation of the constancy of lightspeed, is that the lowest frequency in the universe is 2 over 1. And that means that the highest wavelength is 1 over 2. What are the two quantities in proportion? Einstein said time and space. Is he right or wrong? You don't want to answer that because it's superpositional. He got it. He got it, but there's an interesting aspect to what he got. So the lowest physical number is a two-component number whose Archimedean for the space is 1 over 1, 1 over 1. But that is unity. And so that is not the metric of the space. The metric has to be the split. So it's a split metric to get the space. Well, what space? Well, let's find out. Let's look at the number 1 over 2. Is it less than 1? Yes. Okay. And let's look at the number 2 over 1. Is it greater than 1? Yes. Well, what if you had a boundary called 1? Let's just say it's that circle to which we gave the number proportional 1. It's a two-component 1. It's 1 over 1, 1 over 1. And that's the value of the circle. It's the linear distance around the circumference is 1. That's easy. But we're saying that it's binary 1, which is 1 over 1, 1 over 1. And that's accurate. It's really 1. But in binary space, you should say it's a two-component 1 because it's on the plane. The line is not quite the same because it's open. It goes to 2 infinities. The circle doesn't go to infinity at all. It's unity. So 1/2 would go inside because it's less. It's inside. Well, that's the binary split, is that circle. To the proportion that 1 over 2 is inside, 2 over 1 is outside. And all binary numbers are constructed that way. The only exception to inside and outside is the circle itself. So that's the Archimedean of circular space, is the circle. Can we attach a metric to that? Yes. And that's what nobody was ever able to see. That forms the metric of a new planar space. Because now you can fill the universe with numbers. That's what we do with a Cartesian 2D grid, is fill planar space with numbers on squares. This is not doing that. This is filling the Cartesian planar space with two-component numbers, one of which has to be inside the circle and one which has to be outside the circle, and they always multiply to 1. So they have what's called a harmonic relationship. And that fully and completely, with closure, defines the binary number system, with one interesting exception. What's at the edge? Now, for the line, there are two infinities that are balanced on 0. In this case, there are two infinities, you could say, that are balanced on 1. And one of the infinities goes toward the center and never reaches 0. It's just a number under 1 that's potentially infinitely large. So that's one infinity. Is approaching the center, you can't reach it. That's called Zeno's paradox. It's no longer a paradox, and I'll show you why. It's because of what happens on the outside. As you try to go in with 1 over 4, 1 over 8, 16, it's less and less and less. It never reaches 0 to the same proportion that the numbers outside never reach the highest number. And so you have two infinities that also have the harmonic balance. And this isn't the linear balance on add, which is the operator, and 0, which is the Archimedean center. In this case, you're using proportional space, which instead of having an Archimedean center of 0 on add, has an Archimedean of 1 on a split operator. Right? The other one is split too, it's plus minus. This is not plus minus. It's inside the circle and outside the circle. So instead of having a jump from 0 to 1 to get your metric on the index, you now have a split jump going inside and outside simultaneously on a harmonic relationship between two infinities. So we can capitalize on that insight by assigning a proportional number to infinity and saying it's imaginary. And now we're outside the realm of machine logic, because infinity is a non-representable number. It's interesting, there's a footnote to that as well, which we won't go into now, but it's actually additional excellent information. This will be excellent enough because you'll see the number system for the plane. The number system for the plane. Instead of x and y, which are two linear numbers, you have a single number for the plane. It's a two-component number. Doesn't rely on add. Add does not exist. There's no addition. Although you don't lose it, because the line is the derivative of the circle, and I proved that in 2022. It's already known, it was just never proved the way I proved it. So you do have linearity, which means you have the computable numbers on a derivative object called the line, whereas the circle is unity. It is unity. And if there is a 0 to be used, and I just said there is because the line is there, so there is a 0, it's inside the circle, which is now interestingly characterizable because it's 1/2 of the binary system, exactly 1/2. But where it goes to infinitesimality, the negative infinity, that is a proportion with outer infinity. And they have a specific relationship that they're reciprocal. So when you multiply the center, which is essentially the center of the circle, with the edge, which is essentially the perimeter of circular space, at infinity is reciprocal to the center, to that proportion. So you do need to finitize it if you want to have a representable number system that goes to infinity. You can do that now on this basis that the two infinities cancel on unity. So that means that what's inside the circle will be imaginary to the proportion that's what's outside the space is superimaginary. And they're reciprocal imaginarities. And this is the correct complexification of space. That the center of this circular space is imaginary, and the edge is also imaginary. That's the integral of the space is imaginary to the proportion that the infinitesimal is imaginary, but it's not 0, and you can see why. The reason you can't reach 0 is that you can't reach infinity, and the reason you can't reach infinity is because it has no center. And when you unite those two paradoxes, you finitize the binary system for spherical space. Because whatever applies to the circle applies to the sphere. I also proved that. It's actually the inverse of that. Whatever applies to the sphere applies to the circle. Now you can tell that in both statements I'm missing something. And that is the transformation between the circle to the sphere or the sphere to the circle. Those are obviously also related because one's the inverse of the other in some system. I'll show that to you in the next lecture. I hope you enjoyed this. That completes our proof that all the numbers in the universe are either inside the sphere, which is called the quantum, or they're outside the sphere, which is space. And space has a limit to the proportion that the quantum has a limit. One's the infinitesimal, it can't be zero, and so it is a proportion with infinity. And that solves for infinity. It also solves for imaginarity and recovers complexity into rational space. And that is a mouthful. And with that, I need to eat. My stomach is growling like a bear that just woke up out of hibernation. So thank you for tuning in. Keep looking up. It's a full moon, beautiful. We'll be right back.